Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs, founding director of the Finding Genius Foundation, also host of the Finding Genius Podcast. Today I have Gary Steele. He's a professor in the Department of Quantum Nanoscience in the Kavli Institute of Nanoscience at Delft University of Technology in the Netherlands. So, Gary, thanks for coming.
Our pleasure.
Yeah. So, what I see the topic is quantum circuits and mechanics. What's your research about?
Our research has two main focuses, as you can kind of see in the title. Quantum circuits is one part of what we do. Actually, all of the different research we work on involves quantum circuits in some way. And then quantum circuits are little circuits that we make on a chip in a clean room, a bit like the chips that might be in your mobile phone. Except we make them we do all sorts of tricks to be able to make these circuits behave in a quantum way. And that's why we call them quantum.
What do you mean? So quantum circuit, you mean it uses quantum mechanics to function, or what do you mean?
Indeed, exactly. So the idea, let's say in your mobile phone, you have transistors that are connected together with little wires. And in those wires, generally, the current flows one way or the other way. Or like if you plug something into the wall socket, the current is flowing at any given time. It's flowing out of the socket or into the socket. And that's for us a sort of classical circuits, let's say. But with the circuits that we make, because we make them very cold and we make them in out of special materials that allow us to do this, we can actually make those currents flow in the opposite direction at the same time. And so somehow current is both flowing out of your wall socket and into your wall socket at the same time. And that's something that's only possible in quantum mechanics. And that's what we use and exploit in our research.
Yeah, it might be an elementary question, but how is it different from alternating current?
Yeah, so alternating current, that's a very good question, actually. I have the same problem with bouncing mechanical objects, which is part of our research. So alternating current, it flows in and then it flows back out, right? So there's no net current because it comes out of the wall socket and it goes back in. But say at any given time, if you froze time and took a look at it, then it's only flowing in one way. And
okay.
And what we do is we kind of make the current flow in both directions at the same time.
So does this approximate like an infinite hertz circuit?
In principle, it seems like nothing's happening, right? Or
I just wonder, like if you have a 60 hertz or 120 hertz electricity, would this look like infinite hertz? And what would that do for you if so? I guess that's my question was. I don't know if it even makes sense. But.
Well, let's say the currents that we work with are definitely oscillating, actually. So they are flowing, they're oscillating back and forth and flowing the two different directions. But we make these circuits have these oscillations at around gigahertz frequencies typically.
Okay.
That's actually the same frequency that your mobile phone sends stuff on. So the Wi-Fi in your computer and the mobile signal in your phone, they all work in the same frequency range as circuits, which is convenient because that means our stuff is very cheap because people make lots of equipment.
Yeah. What are some of the benefits of the circuits that you're creating in your own way?
So one thing that people try to do with these quantum circuits is to make what's called a quantum computer. And so, in principle, if you have these circuits that can be doing two things at the same time, then you can make a computer. A regular computer is made up of transistors, which are 0 or 1, and if you can build this quantum superposition thing into the bits you're working with, then your computer can also be, both 0 and 1 at the same time. And it's actually quite a technical, weird thing, but it turns out that that's a really big deal for the way computers work. And some people in the 80s discovered that if you could actually, theoretically, they started to look at this idea, and they discovered that there are certain problems that can be done exponentially, really much, much faster on a quantum computer than on a classical computer.
Well, I've heard there's a lot of challenges, with quantum computing. It has to be kept very cold. Has to keep noise out. The error rate can propagate and cause all kinds of problems. I mean, it seems like they're very delicate systems. So what, these circuits you're creating, I mean, are they sustainable? Can they stay in their coherent state for a long time? I mean, how far along are you towards commercialization?
Well, so, I mean, my research itself is not so focused on implementing it towards building a quantum computer. That's actually sort of left the hands of scientists these days. So that's actually much too big a task for scientists on their own to tackle. And actually, the main people working on that now are companies. So this is something where companies like Google and IBM and also some smaller startups like Rigetti in California, and actually startups all over the world. But it's really become an industrial type of challenge, engineering challenge, that goes beyond what we can do in the lab as scientists, let's say. And we can make a few qubits. My group is not super hyper specialized in this, but we can make a few qubits, and we can get decent coherence times. But putting that all packaged together into a very, very big scale computer is extremely tricky. That nowadays, right, is really a challenge of engineering. And for that, you need a big team of lots of people and lots and lots and lots and lots of money.
So are you innovating? I mean, what are you working on in regards to quantum circuits? Are you innovating to make them more reliable, or work at higher temperatures, or what's your push?
So we've been looking at I'm sort of quite a fundamentally driven scientist. I'm very curiosity driven, and what we try to look for is funny little places in these quantum circuit territory where we can do creative new things with the design of the circuits. Not bounded by the constraints of trying to make a scalable quantum computer, but asking questions like, well, what if you just do this in a completely different way? What if you think about the circuit in a way that people don't usually think about, and connect these pieces together in a different way on the chip? Is there a new type of stuff that you can do with that? And that's a big push of where we do our quantum circuit research.
And you talked about mechanical oscillators. I guess that I didn't hear what you had said before, but you're working on some kind of oscillator that uses quantum mechanics. Yeah.
So the second sort of pocket of research, focus of research in the group is to try to build devices where we can show effects of quantum mechanics in mechanically vibrating objects.
Okay. So what's an example, and what's the consequence of that?
So you can think about like a little vibrating drum, for example, or maybe not so little vibrating drum, where we are trying to, in the quantum circuits, the thing that we're making quantum superpositions of is the currents that are flowing in the wires, for example, but the wires themselves are just stuck on the chip, and there's currents kind of flowing around back and forth if you want, but. In the mechanical part of the thing, we're trying to actually make a mechanical object be in a superposition of being in two places at the same time.
In two places, meaning along its vibrational path, it's at two places that it normally would vibrate to, or what do you mean?
That's right. So, there's a sort of animation that I usually use in my talks, where think of a drum that's bouncing up and down, right?
Okay.
But then imagine that there's sort of a twin copy of that drum that's bouncing up and down exactly out of phase. So that when one of the twins is going upwards, the other twin copy of the drum is going downwards. So it's kind of, as a function of time, it's kind of bouncing out of itself and then back in again, and then bouncing out of itself and then back in again. I don't know if that makes
Okay.
sense.
Yeah. No. What would be the use of creating something like this, though?
One of the things that we're driven by is that if this thing that is vibrating is heavy enough, then in principle, the one of these twins will exert a gravitational force on the other one. So there's these experiments where this Cavendish experiments actually, where people measure the force that the gravitational force that two balls pull each other with. This is a force that makes Earth go around the sun and the moon go around the Earth. This is typically a force that happens on really big objects. But if we can take these little vibrating drums and push the drum out of itself, then in principle the drum should be both exerting a force and not exerting a force on the other pair at the same time. And this allows us to test concepts of combining quantum mechanics with gravity. And that is actually one of the fields of physics that people really don't know. That's sort of an open standing question in pretty much all of physics, is whether or not people can combine quantum mechanics. And
you would have two oscillators that are coherent in their oscillation, or they anti-coherent, or what do you mean?
So it's one thing, but it's both vibrating up and down at the same time.
Oh, so you want to see, because of creating, okay. So by creating this quantum state where it's both vibrating, let's say, I'm just going to call it up and down, it may take on the appearance of two objects, and therefore they may exert gravity upon each other?
That's right. So we kind of know from electro, if you did this with, of course, if I have two charge objects, they will do that as well. The answer is that, so you might say, oh, that's really weird. I'm going to have an electric field that's in the quantum superposition of pointing up or down. But that's fine, actually, because people know how to make electric fields quantum mechanical. But actually, nobody knows how to make gravity quantum mechanical. And there are even some conjectures that maybe this is where classical physics comes from, is from that gravity and quantum mechanics are not compatible. And so we think that with these very tricky experiments, with these little funny drums that are bouncing up and down at the same time, we could start to test some of these theories that say that quantum mechanics should break down when gravity becomes in a quantum superposition.
When you say drum, you mean a macroscopic drum?
Yeah, these things are pretty big. So the ones that we work right now with, they're sort of both macro and nano. They're about 1 millimeter by 1 millimeter. It's sort of a stretched membrane that's a square, about a 1 by 1 millimeter, but it's only 50 nanometers thick.
Okay.
So and those are, so it's macroscopic in that you can see it with your eye. It's also very thin, but that's a little bit the idea. That whole thing is going to bounce up and down, and we want to build it in a quantum superposition, bouncing up.
But how do you cause it to oscillate? You would have to, I guess, hit it with a pulse of electricity, or mechanically move it, or do something, right?
Yeah. So we can actually make it oscillate pretty easily by just pushing on it. We don't push on it with our finger, but we put it up into a circuit, and then if we have for example, if you put a little capacitor nearby, and the drum is typically metal coated, then if I put a voltage on the capacitor, I can attract the drum. And if I start putting oscillating voltage on that capacitor, I can make the drum bounce up and down. I don't know if that makes any sense to you, or you can.
Yeah, no, I know. So you're driving it electrically, okay?
Exactly.
It's oscillating at a frequency you decide, right?
Exactly, and we pick to drive it at its resonance frequency because then it vibrates really large. But that's actually not enough, because actually we want to somehow kick it both up and down at the same time.
Right.
And that's actually pretty tricky.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
And
how'd you do it?
So, well, we haven't done it yet, unfortunately. But For that, actually, we want to actually borrow from the world of qubits, because the little quantum circuits I told you about before, that's actually the whole basis of how the quantum computer works. The quantum computer is all about making devices where electric fields are in a superposition and pointing upwards and downwards.
What about taking a molecule, though? I mean, all atoms, I guess they vibrate, so they act like that drum in a way, right?
Yeah.
I don't know, they all have their own frequency.
Yeah.
Why have to set up an artificial system? Why not just use a molecule and try to achieve this coherence in one of the bond vibrations, between two atoms?
Yeah, that is absolutely possible, and people have done that actually for for a long time in solid state, in atomic physics with gases, and then there's this super amazing stuff that people started doing in the 80s and 90s, and atoms where they could actually catch a single atom and do that with a single atom. But the problem is that the mass is just too small. So the gravitational force, it scales. There's sort of this time that it would take for the gravity to affect the quantum evolution, let's say, sort of that time scales with the fourth power of the mass. So if you do the calculation for an atom, like an electron in an atom in a chemical bond of an atom or molecule, then the amount the amount of time you'd have to do the experiment is something like 10 to the 18 years.
But you have to mechanically drive this larger setup. So, like, how do you get it into a state where, again, it's vibrating one way and another at the same time? Like, how would you, how are you going to do that?
So for that's what we do is we actually we have the sort of, we can pull and push on the membrane with an electric field, and then with a voltage basically on an electrode, and then we use our qubits to make that voltage into a superposition of being a positive and a negative voltage, and we make that voltage then oscillate in this weird superposition where it's
also. So you're driving the membrane. You're driving the membrane in like a quantum mechanical way, meaning you're feeding it opposite voltages at the same time. Is that what you're doing? And so
that's pretty much exactly what we're doing, and then we use the qubits to make these funny, weird opposite voltages at the same time. That's the basic idea, exactly.
But what kind of cascade do you get? Like when you hit a membrane with a voltage period, I would think there's like cascading effects. It doesn't, all the electric or the energy doesn't immediately go into the membrane. Some of it's lost, and there's secondary effects. So I would also think it would be very hard to time any driving motion, to be exact. So if you're hitting it with opposite voltage, I mean, even if they're like a picosecond apart, wouldn't that disturb your ability to put it in a quantum state?
Yeah. So what we do is we wouldn't, I say hit, but we usually hit them very gently. And what we do is we sort of turn on we slowly turn on an oscillating field that then sort of gently rings up the membrane, but it's always oscillating in such a way that it's sort of positive and negative. That's sort of our little trick.
Have you been able to do this? I mean, is it working where it's, I would think you'd have to drive it, and then I guess the echoes of the vibration may be coherent, but not the initial driving vibration itself. Or maybe I'm wrong. I don't know.
No, yeah, indeed. I mean, so if you just turn on the driving immediately, then you'll have all these annoying transients, and it'll be a big mess. And so that's why we always have to sort of ramp it on carefully to sort of it's sort of like if I hit if I hit a pendulum with a hammer, it kind of goes a bit nuts, right? But if I sort of tick it very slowly, a little bit harder every time, then I can get it into a nice oscillation.
So how far along have you gotten? Have you done this, and have you observed physically that the membrane is in two positions at once?
That would be fantastic if we have. Unfortunately, we are discovering these are very tricky experiments. And some of them are physics tricky, like the physics of how to make the qubit push this membrane two directions at the same time without blowing up the qubit or causing all sorts of other chaos in our circuits. That's very tricky. but also there's really boring, mundane, tricky things like we basically take this chip and we turn it upside down and it's super low tech. We glue it actually to another chip that has our qubits on. And then sometimes they just break and sometimes they don't. And then sometimes you have sort of a bad spell of about 3 years where they break all the time. And so, it could be demoralizing for a generation of PhD students who've discovered. But it's one of these things where the devil of this is really in the details. It's really about little tiny things that are quite important to make sure that the membrane can oscillate for a long time without losing its energy, and that you don't smash it when you turn the screws to push it a little bit closer, and all sorts of that's what keeps us busy in the lab every day. This type of stuff.
So what do you think will happen once you get it to work? I mean, like what's your guess? How long, if you get it to work, will it last for like a microsecond? Like what's success look like?
So what we've done from the data we've taken before on the ones from several years ago that weren't exploding all the time, we were able to show that the devices, this oscillations of this weird, we call it a Schrodinger cat because it's a sort of like a big object in two places at the same time. This mechanical Schrodinger cat, he should live for something like 100 milliseconds. And so if there's no effect of gravity, then he should live for 100 milliseconds, and we should turn on an experiment. We should see that this thing is coherent for 100 milliseconds. And if you sort of believe the somewhat, shot in the dark guesses of some smart people about what might happen with gravity, then they would tell us that gravity should actually kill our quantum superposition in times of about 10 milliseconds. And so there we have a good, reasonable margin, about a factor of 10, where we should be able to to see whether or not, quantum, gravity is really, like some people suggested might, destroying quantum coherence.
How far apart will the two positions of the oscillation be?
They will not be very far apart. So they will be about 7 femtometers.
And at first, I guess it depends on how you catch the oscillation, but it'll be an expanding and then a contracting distance too. I mean, it'll be changing.
Right. Yeah. And the peak distance will be we're targeting is about 7 or 8 femtometers.
So what kind of forces will be in play during the expansion phase of that space and the contraction phase? And what will that do? So
the idea is that as it pulls apart from itself, basically what the trick is that we need to pull the nuclear diameter out of itself, because the nucleus is where all the mass is. So once we get and if they're overlapping, they obviously can't exert a force on each other. But if we can pull the nucleus, displace the nuclei by more than their diameter, then there should be gravitational energy. It should be gravitational sort of force field coming out of the nucleus. And then if we can get that nuclear mass density out of each other, then the gravitational field is both pointing up and down at the same time. And
essentially, I mean, they're going to be a much smaller distance apart than the size of, like, the radius of a nucleus, right? Or the diameter of a nucleus. I'm sorry.
So the diameter of nucleus is something like, in our materials, is something like 3 femtometers.
Okay, so they'll be just about touching. Let's say, I'm just using the wrong language, I'm sure, but if I imagine like 2 atoms and I just picture them as like, a hard center is the nucleus and then a cloud around them. So the 2 hard centers will be essentially like edge to edge at the widest point of the oscillation, and then they'll overlap for the rest of it, or what will it look like?
That's right.
Like a Venn diagram of atoms.
Yeah, they'll be a little bit bigger than so the diameter is something like 3 femtometers and the distance is 7. So there's about a 3 femtometer gap between them of nothingness. And and that's where our gravitational field will be both pointing, up and down at the same time.
So do you think that this will, I have no clue, but will this give off like a gravitational wave, or can you measure, I mean, besides time to collapse, what will you be able to measure from this? Do you think it'll give off anything?
Most likely it'll probably do nothing. Our best case scenario is that that nothing will happen, and that the thing will just be coherent still. And if we can see that, then we've shown that, at least in some, that gravity is, it is possible to create, a space-time that is in a quantum superposition, let's say.
So, I mean, within I don't know, if you just pick an atom, a hydrogen atom, the electron is moving in how big of a space, and essentially it's coherent within that space, right?
Yeah, the electron is about an angstrom, so that's a lot of femtometers.
Yeah, it's like 10,000 femtometers, right?
That's right. Yeah.
So essentially, it's moving in this in this scale, a gigantic space in a quantum mechanical way, right?
Yeah,
it's existing, absolutely. Or oscillating, or
yeah. But that in sort of this sort of gravitational picture, that's not a big deal because electrons are light, and so is sort of the predictions for how long it would take before this sort of crazy theory that gravity might be incompatible with quantum mechanics. How long it would take that theory for that to decohere the electron is sort of longer than the humans have been on Earth or something.
So what do you think? I mean, do you think a larger oscillation would make it easier? Like, what are some of the parameters that will get you closer to what you want? Are you having issues with like the temperature, or like what's troubling you right now?
So temperature, aside from really boring things like things snap and crack and break, and one of our problems is temperature. So the frequency of our mechanical oscillations is like 100 kilohertz to a megahertz or so, something in that range. And we cool things down. We buy the most. We spend €500,000 to buy this big, huge piece of equipment that gets us to an absurdly low-sounding temperature of 10 millikelvin or so. That's 10 millionths of a degree above absolute zero. But
millikelvin or microkelvin or
10 millikelvin. But that's not cold enough, because at 10 millikelvin,
no, that's like hot.
That's mega hot. So
what's the, by the way, just out of curiosity, what's the coldest that anyone has ever been able to get a system? Is it now like picokelvins yet, or what? Is it microkelvin or what?
It depends on what you call a system and what you call cold. That's a very good question. So people are able to cool the center of mass motion of atoms in a vacuum chamber using laser cooling to nanokelvin. But that's sort of 1 degree of freedom of the atom, right? It's a little bit, and whether an ultra hyper dilute gas of atoms, or the atoms aren't touching each other, whether that's a material or not, that's sort of an interesting, possibly philosophical discussion. And it typically limited to something like 10 to the 5 atoms. So what we buy is a machine that uses liquid helium and mixtures of helium-3 and helium-4. That helium-3 is a gas that costs a bloody huge amount of money, to cool just a huge block of copper, like kilograms of copper, to 10 millikelvin. That's sort of conventional cryogenic cooling, and that's where we always start. But for our oscillators, because of the low frequency, they'll still have like 1,000 thermal quanta. We're like 1,000 quanta away from the ground state when we start. So how we can get colder then by using similar tricks. We actually use tricks that we borrowed directly out of the textbook of atomic physics, and we do laser cooling type of tricks to cool our mechanical devices. Much so that the noise of the vibrations is much, much lower than 10 minutes. And the record we reached in our group is about 35 microkelvin of vibration.
Yeah, so you're trying to remove the natural vibrations of the material itself, so that only the oscillation is important, right?
Yeah, but we're only cooling, it's kind of a funny thing. All the other, if you think about a string, it has sort of the fundamental mode and has higher harmonics, for example, like that where it wiggles more, right? We're actually only cooling one of those. All the other vibrations are still vibrating like crazy, but we're cooling only one of them. But as long as they're linear and they're orthogonal to each other, and then that's fine, because one can be cold and the other one can be hot, and they don't talk to each other.
Oh, because you just care about the oscillation in just one dimension so far.
That's right. We care about the oscillation in one dimension, and then only one mode of that. So that
I mean, with that,
some tricks.
I don't know. It's just with that tiny distance of oscillation. I mean, how do you know that the two oscillation modes will line up, along the same axis, so the distance is truly right? And I mean, I don't know, it just seems so hard, so complicated.
It is a bit complicated, because also when we're making this little quantum, when we're making this sort of quantum superposition, the other modes are still bouncing up and down, right?
Well, are there materials that have fewer modes? Would that be an easier starting material? Or I'm sure there's trade-offs, but...
Yeah, that's something we also work on. I mean, you have too many modes, and you can engineer the modes just by changing the way, the shape of the membrane, for example, or how you pattern it. That can also help a lot, and it can be a real pain if you have too many modes that are bouncing. But it's kind of a weird thing, but it really does work that these all just add linearly, so you don't really care if your superposition is completely still or if it's bouncing up and down on top of another mode.
Really?
Yeah.
So it wouldn't be useful to have a crystal, some kind of crystal that has a certain structure that preferentially biases, very few modes of motion, or one more than others?
Yeah, I mean, that always helps, but it's not a killer if you have other modes, it turns out.
Okay.
You can live with them, actually.
Interesting.
It still makes my head spin sometimes, and sometimes I get myself into a loop thinking about it. But yeah, we have to trust the mathematics, and the math tells us it works, and then our intuition feels.
So what does this tell you? Let's say you do it, it works. What are the possible things that you could learn from doing this?
So the best case scenario. Let's say the best case scenario is we discover that really there is a fundamental limit to how much gravitation can play a role in your quantum evolution, and then it screws everything up. That would be super cool. That one's kind of hard to prove, because we'd have to do lots of control experiments to really show that that's the case. But that would be very interesting. But I think personally, I believe very strongly in quantum mechanics, and probably that gravity is probably compatible with it. So then you end up with a very pessimistic possibility that nothing could happen, and we just say, okay, it works. But the mathematics of this is very tricky to work out, actually combining gravity with this quantum evolution. And so there's sort of also maybe a hope that we'll see something that is maybe not expected, and that we could actually learn something about how gravity is modifying the evolution of the wave function by looking at what we see in the way this little thing is bouncing up and down.
Do you think you get any insight into gravitation itself from doing this?
Well, I mean, certainly the fact, the insight whether gravitation is even possible to combine with quantum mechanics would be a pretty monstrous revelation in physics. There are also, if we can really do this type of experiments, aside from whether or not quantum mechanics is compatible with gravity, we will essentially be able to probe this gravitational field that's at a distance of some femtometers from the nucleus, and that is people typically imply gravitational effects from looking at stars or planetary motion, and that will be a very interesting thought as to whether we could start to learn about how gravity behaves on length scales that people have never really looked before. I'd have to really think about whether that's possible. But that's certainly something that puzzles us and drives us.
So if someone asks you what is the sound of one hand clapping, you take it very seriously, right? Cool.
It is actually really like one hand clapping, actually.
Actually, I just thought of something. The is this oscillator is going to be in a vacuum or no?
Yeah, we keep it in sort of cryogenic vacuum. That's important.
Is there any way to to observe the oscillation and that it'll create a slight pressure differential on the wall behind the oscillator as it oscillates, or a slight increase in vacuum? Like, can you look at the nature of the vacuum? It's not a perfect vacuum, but can you look at the nature of it, and maybe the conductivity of the vacuum around it will change as it oscillates? I mean, is there any way to look at other factors to tell you what's going on?
Let's see. I do have some colleagues actually who are trying to put pressure, doing these types of experiments with liquids actually, with superfluid helium has become a big topic in the field, where they really do have little pressure cells in their cryostats and combine these little membranes with little liquids, superfluids actually. The vacuum itself is also an interesting beast because the vacuum, is also not empty, right?
Right.
And so these types of experiments are also interesting from the perspective of trying to look at things like the Casimir effect. I don't know if you know much of, if you've heard of the Casimir effect before, or
yeah, that's why I asked. Yeah.
So indeed, the idea is that if you have two metal plates get really close, then the sort of 0 point energy results in an extra force that pulls them. And I have colleagues that have also done experiments like this, and from these types of because we have to be able to do these experiments, we have to be able to sense this position of this plate down to like sub-femtometer accuracy. And so if you have some way of pushing that plate up and down, you can start to look at how, for things like Casimir forces could play a role in the position and stiffness of the plate. And I have some colleagues in NIST who have been doing that by using a DC voltage to also pull the plate and statically displace it. And they've actually done it's funny because it's sort of a side remark comment in their paper. And this thing over here is because of the Casimir force. And so that's certainly something that people have been looking at, is using these tools of optomechanics, that is what this is called, where we detect the position very sensitively to look at things such as Casimir forces.
Yeah. Well, very good. Gary, what's the best way for people to find out more about your work and to keep tabs on it?
That's a good question. So we have, you can always read our papers.
Where can they feel every oscillation of your work as it happens?
So we we try to keep a little bit up on press releases, and those you can find them on our department website. Usually we profile all the press releases from our work, but it's something we're interested in, is learning how to communicate this better to people. And so we're thinking we're going to get a new website design, and we're going to see if we can find time and manpower to maintain a blog where we talk a little bit more about the work we do.
Okay. Well, very good, Gary. Thanks for coming. It's it just takes a little while to figure out what's going on, but I appreciate you explaining it, and thanks for coming on the podcast. I appreciate it.
Thanks for having me. I hope I had some success in bringing across what we do.
Right on.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.